Hello, I am Sarbashis Kumar. Today I teach you condition for a Subrings and another. If S1 be Subring and S2 be Subring, then its intersection S1 intersection S2 be Subrings. So my first proof condition for Subrings. Before starting my proof, I am interested to say, if you like my video and my teaching, please subscribe my channel. The necessary and sufficient condition for a non-empty subset S of a ring R to be subring of R. If A belongs to S, B belongs to S, then A minus B belongs to S. Number 2, if A belongs to S, B belongs to S, then AB belongs to S. The conditions are necessary. The condition are necessary. Suppose S plus dot is a subring of R plus dot. Then S is a group with respect to addition. S is a group with respect to addition. Okay, we know since S is a, suppose S is a subring, if we assume that S is a subring of R plus dot subring of R plus dot, then S is a group with respect to addition. We know if B belongs to S, then minus B belongs to S. So A belongs to S, B belongs to S. This implies A minus B belongs to S. Again we say S is closed with respect to multiplication, as we assume that S is a subring. So A belongs to S, B belongs to S, that means AB belongs to S. Hence the condition is necessary. Now the conditions are sufficient. We have to prove that condition is sufficient. Here we suppose that S is non-empty subset of R. The condition of 1, 2 are the satisfied. Here we think S is a non-empty subset of R, so condition 1 and 2 must be satisfied. So A belongs to S, A belongs to S, that means A minus A belongs to S. It means 0 here minus A. Here, so 0 belongs to S, it means 0 is the elements of R. We have to prove now that S is a subring. So it is one condition, 0 element is belongs to S. Now 0 belongs to S, A belongs to S, it means the condition 1, oh sorry, here not minus A, and because A minus A belongs to S, this is the condition. Here 0 belongs to S, 0 belongs to S, A belongs to S. This implies 0 minus A belongs to S, that means minus A belongs to A. S. Each elements must have additive inverse. Each element must have additive inverse. Now since A, B elements of S, then minus B belongs to S. So A belongs to S, minus B belongs to S. So A minus B, so A plus B belongs to S. So A is closed with addition. This is the condition of subring, that is 0 element and inverse element and addition. And since S is closed with respect to addition, thus associativity and commutative must be held in S. So S is a abelian group. So this is the first proof, first part of a ring, and S is close to multiplication. So S is associativity, associatives of multiplication and distribution must hold in S. So since hold in R, since it hold in R, S is a here we assume that S is a subset of R, and S is closed with multiplication. Since associativity and multiplication and distributivity of multiplication must hold in S, since it hold in R, so S is a subring. So this is my first proof. And my second proof, the intersection of two subrings is a subring. Since let S1 S2 be subrings of R, we have to prove that sufficient condition. If F belongs to S1 meet S2, B belongs to S1 B S2, then A minus B belongs to S, because this is the condition of subrings that we prove above. So intersection of two subrings is a subrings, then we have to prove this condition, these two conditions. A belongs to S1 S2, B belongs to S1 S2, then A minus B belongs to S1 S2 intersection. Number 2, A belongs to S1 S2 intersection, B belongs to S1 S2 intersection, then AB belongs to S1 S2 intersection. So we have to prove this. Number 1, we have to prove first, and second, how prove? If S1 is a ring, then if A belongs to S1, then A belongs to S1 and A belongs to S2. B belongs to S1 S intersection S2, so B belongs to S1, B belongs to S2. And now we know that S1 S2 both are subrings, then its intersection will be subring, then it hold these two conditions we have to prove. So since S1 is a subring, then A belongs to S1, B belongs to S1, then A minus B belongs to S1 and AB belongs to S1. A belongs to S2, B belongs to S2, so A minus B belongs to S2, AB belongs to S2. So if A minus B belongs to S1, and since this is a subrings, so this we assume that S1 S2 are subrings, and that's why this is the condition. A belongs to S1, B belongs to S1, A minus B belongs to S1, AB belongs to S2 S1. A belongs to S2, B belongs to S2, so A minus B belongs to S2, AB belongs to S2. And now A minus B belongs to S1, A minus B belongs to S2, then A minus B belongs to S1 S2. AB belongs to S1, AB belongs to S2, so then AB belongs to S1 S2. Thus here we find A belongs to S1 intersection S2, B belongs to S1 S2, then we find A minus B belongs to S1 and AB belongs to S2. This is the condition of a subring, then it holds, and so S1 is intersection S2 is a subrings. And we prove this as because S1 S2 both are subrings, then it holds the condition, and from this we prove. Thank you so much.